Okay, so hi everyone. This is a video on quantum mechanics. So if you are still bothering to watch my videos, I have been on a long break, I know, and I will continue with the statistical mechanics series later on. But this video is about quantum mechanics, and I'm going to discuss a result that I found particularly very interesting as I was preparing for my quantum mechanics final exam. So let's get started. But before that, I'll try to just list down the prerequisites that you need if you want to follow this video. But the final result is very beautiful. So if you can follow the video, then that would be like very interesting for you. So first is that you should know a little about linear algebra, about the concept of basis and the importance of a basis. Along with that, you need to know about the gamma function, and along with that, you need to know some basic quantum mechanics, and you also need to know the harmonic oscillator, the quantum harmonic oscillator, and its treatment using the creation and the annihilation operators. Okay, so this is the creation operator, and this is the annihilation operator. So, with that being said, let's get started. So, what we are going to talk about today is something called the coherent state. What a coherent state is, and why I particularly made this video will be clear by the end. So, first of all, let's get started. So, now, first of all, let's talk about the concept of completeness or closure relation. Okay, so a lot of times in mathematics, the word completeness might be used in a different context. So I'm sorry, this doesn't fit here, but the word closure is the word that I was looking for. Now, suppose that you are in a vector space and you are suppose in a finite dimensional vector space, and suppose that you have chosen a basis. So now I'm going to denote my vectors by this. This is the first basis vector, this is the second basis vector, and so on. Okay, so let's say that my vector space is n dimensional. So if the basis has been made orthonormal, so I can write the identity operator using that basis using this. Okay, so since there are n dimensions, so there will be n basis vectors, and we have this. So in a nutshell, what we can write is kk, and k is starting from 1 to n. Now it might also be possible that we start the convention from 0. So in that case, this will become n minus 1 and this will become 0. Okay, so the identity operator will be this. So this operator does nothing to any vector that you apply it to, and it gives you the same vector itself. Okay, so this is one important thing that we need to know before we go forward with the main meat of this video. Okay, so the second thing that I'm going to talk about is the creation and annihilation operators. So this is the creation operator A dagger in quantum mechanics, and this is A. Now, suppose that we are in the uh, first excited state of a quantum harmonic oscillator. So it is written like this. So this is known as a Fock state. Fock state. And suppose that we are in the nth excited state, so we write like this. Now, what this operator does is, if it acts on any Fock state n, so by definition it acts like this. So it takes the Fock state n and it takes us to the Fock state n plus 1 with a scaling constant root n plus 1, not very important. Okay, and if the creation operator, okay, so this is the creation operator, and what does the annihilation operator do? This takes us one Fock state back. So this is under root of n minus 1, and this is not a writing error. There is this asymmetry between the two. Okay, so this is it. Yeah, so now first of all, as I have already introduced the Fock states n, So what is the closure relation for them? First of all, the space of the quantum harmonic oscillator states, this is not a finite dimensional space, but this is an infinite dimensional space. So the closure relation will take the form n equals 0 to infinity is equal to I. Okay, so this is one very important bit that we needed to learn. Okay, so now let's talk about the coherent state in quantum mechanics. Okay, so what is the coherent state? Now, in quantum mechanics, what we have is we have these operators A, which is the annihilation operator, this its Hermitian adjoint, which is the creation operator that I already talked about. Now, if we notice clearly, if we look at these equations, we can see that the Fock state n is not an eigenvector of the creation or annihilation operator. Okay, so I think I made a writing error here. Sorry. Yeah. So this Fock state n is not an eigenfunction of this annihilation operator or the creation operator either, because this takes one state up, this takes one state down. So now the question is what are eigenstates of A? Okay, very simple question, and we need to find an answer to this question. And by the end that I derive the states of the eigenstates of A, it will be very obvious why they are the eigenstates and nothing else. Also, there is something interesting about the eigenstates of this operator, and so that the explanation for which we will say for another day. But for now, we are going to focus on the eigenstates of only A. Okay. So now let's do something. So A, let's say that this is the eigenstate of this, and we get a particular eigenvalue lambda, and so this must be the eigenvalue equation for the annihilation operator A. And now we just need to find out what this eigenvalue lambda is and the eigenvector corresponding to it, that is ket lambda. Okay, so I'm going to make a claim now. The claim is a very simple one, but it's nevertheless very interesting, that the states corresponding to e to the power z, where z is any complex number, z is any complex number so this state is an eigenvector of the annihilation operator A with the eigenvalue z. Okay, so since I've already said that z can be any complex number, that means that there are an infinite number of eigenvectors of A as well, right? So now let's prove this equation very quickly. It's not a difficult one. So for this, we are going to use the definition of exponential of an operator, which we use the Taylor series for. So e to the power z a dagger 0, the ket 0, is going to be defined as z to the power k a dagger to the power k upon k factorial, all being applied to the state 0. So nothing technical in this. This is just the Taylor series of the operator. Okay. So now k equals 0 to infinity z to k upon k factorial. Now a dagger to the power k on 0. Okay. So now if we apply a dagger to 0, we get 1. If we apply a dagger, okay, so I should probably scroll up to the formula for how this acts on a ket Fock state. A dagger on this works like this. So A dagger on 1 acts like square root of 2 like this. So in general what we're going to see is A dagger to the power k on 0 is going to be equal to the square root of k factorial times the state k, and this is precisely what we're going to replace it with. So square root of k factorial A square root of k factorial times k. Now this can be brought down here. Okay, so now let's apply the annihilation operator on this. Now A applied on this and see what we get. So k equals 0 to infinity. For the sake of some simplification which will come to be obvious later, we are not going to cancel these just as now. So z to the power k upon k factorial, and I'm going to keep this square root of k factorial right here. And now let us apply. So since a is a linear operator, we can simply bring it inside. So in order to save some space, I'm going to do it here. Okay, so now what does this do? So k equals 0 to infinity z to the power k square root of k factorial square root of k and k minus 1, and then k factorial up. Okay, so now let's do something which is a little tricky to get in the first place. Okay, so first of all we have to remove this k equals 0 starting point, because then it will become a negative state and this won't make any sense. So k equals 1 to infinity z to the power k square root of k minus 1 upon square root of k. Okay, so what is this? Square root of k factorial. Okay, now now we do something which is sort of a cheap trick, but nevertheless it works really nice. So k minus 1 upon square root of k minus 1 factorial. Now we can take this z outside, and by a change of the dummy variable we can simply make this p equals 0 to infinity z to the power p upon square root of p factorial, right? I hope this is okay. So from here what we are going to get is p equals 0 to infinity z to the power p upon p factorial times square root of p factorial p, and it does not take long to realize that this is simply a dagger applied exactly p times on the get state 0, and this is nothing but just so we have proved that this state is the eigenvector of the annihilation operator with eigenvalue z, and z can be any complex number. I'm claiming z to be any complex number again and again, so because there is a reason for it. The derivation that I'm going to do from this point on is extremely beautiful, and it's going to make use of the fact that z can be any complex number. Okay, So now, okay, we have done all this, but now you may ask, what is the use of all this? Okay, so we're going to talk about the use just now. Now, we have already talked about how to write the closure relation using the Fock states of the quantum harmonic oscillator. We've already talked about how this is equal to identity, and but now I ask a very simple question. How am I going to write down this closure relation in terms of the coherent state Z? How do I write down this closure relation in terms of this vector? Okay, now this is the only thing that we will focus on from this point on, and I'm going to make a claim. I'm going to make a claim, and then I'm going to prove it that that is the correct closure relation if we want to write it in the form of the coherent states. So okay, so this state of the eigenvector of the annihilation operator, this is known as the coherent state, and the reason it is called a coherent state, okay, so this reason is particularly interesting. So this is the wave function, this is the wave function, or the state more precisely, of a beam of light, going with a fixed wavelength and frequency, obviously. So a perfect monochromatic beam of light is represented by this state in quantum optics. So, but that is not the point. The point is this is equal to I, and the claim is that this closure relation is written like this, is written like this for the coherent states, and I'm going to prove it just now. So this integral is over the whole complex plane, the xy Argand plane that we know from complex analysis, and now precisely because for every z you can find an eigenvector corresponding to the annihilation operator, we can integrate along the whole complex plane and make sense out of this integral. So this is why the fact that you can choose any z was important. Okay, so now let's try to prove this difficult looking relation, but we're going to use the trick of polar coordinates, and this will just become very simple. So okay, so now let's do something like this. Now let us break up this integral into polar coordinates, and let us also write z in the terms of Fock states, because we are going to use that later on. Okay, so I just want, okay. So first of all, let's write z in the form of the eigenstates of the quantum harmonic oscillator, that are the Fock states. Now we have already seen that the eigenstates of the quantum harmonic oscillator, so the coherent state when expanded in the form of these Fock states looks something like this, right? So let us just replace them here. Dx dy upon pi, and what was this again? Okay, z to the power k, get k upon square root of k factorial. So k equals 0 to infinity k upon square root of k factorial and get k. So this is just z. Now this is a ket and this is a bra, so we have to invert this in a sense, and we'll have to use a different dummy variable. So let's take this to be m equals 0 to infinity, and let's write this z complex conjugate to the power m upon square root of m factorial. and as usual we have e to the power minus mod z square. Okay, so far so good. Now, so what we are going to do now is we are going to bring this integral inside, and we are going to take those summations outside, and I hope you all know that we can do this. So k equals 0 to infinity, m equals 0 to infinity, and so this is k, this is m upon square root of k factorial m factorial, and okay, I hope I haven't missed anything. This, and this. Yes, I haven't missed anything. So dx dy upon pi, and z to the power k, z bar to the power m, e to the power minus mod z square. Right? So since we have to integrate over the whole complex plane, let us break this up into polar integral. So for converting this to a polar integral, we are going to use this relation z equals r e to the power I theta, where theta is the polar angle and r is the modulus of the complex number z, and so this dx dy will simply be replaced by r dr d theta. And okay, so let's do this instead of speaking. So k equals 0 to infinity, m equals 0 to infinity, k m upon square root of k factorial m factorial, r equals 0 to infinity, theta equals 0 to 2 pi, r dr d theta upon pi. Okay, so this might be a little tricky. So z bar in that case is written as r e to the power minus I theta. So we are just going to do that here. So r to the power k plus m, e to the power I theta k minus m. This minus comes because we have put a minus sign here. And this is simply e to the power minus r square. Okay, very nice. Now, since there are no cross terms between r and theta here, we can just separate out the two integrals, and yes, so first I will write down just for r, and after this the one for theta will become very clear. R dr upon pi, r to the power k plus m, e to the power minus r square, and along with this we have theta going from 0 to 2 pi, e to the power I theta k minus m d theta. Okay, first of all let's talk about this one. It is a very interesting integral and not a very difficult one. So let's talk about the condition when k is not equal to minus m, k is not equal to m. Okay, so if k is not equal to m, this integral will simply become 1 by I theta k minus m. Sorry, this theta will not be there, it's the dummy variable. And so we will have e to the power 2 pi I k minus m minus e to the power 0, which is just 1. Now, okay, now looking at this, we know that k minus m will in any case be an integer only. It will not be a fraction. So we can be sure that this is a multiple of 2 pi I. Okay, so this is 1 and this is 1 and this becomes 0. So for k not equal to m, this becomes 0. How about k equals to m? So when k is equal to m, this whole power will become 0 and the integrand will be just 1. So 0 to 2 pi d theta will be just 2 pi. Okay, So this integral as a whole, as we have already seen, can be replaced by the Kronecker delta and along with it a factor which scales the integral. So I don't think that it is very difficult to see that we can simply rewrite this integral as 2 pi delta k m. Okay, so when k is not equal to m, this is equal to 0, and when k is equal to m, this is equal to 1, and so 2 pi is the whole integral. Now the beauty of the whole proof comes around here. So that pesky pi in the denominator was actually there to cancel with this. Okay, and let's bring that 2 here, because now the power of gamma function is coming. And okay, so now there is something else that we need to realize. Okay, so write this delta km here, delta km. Okay, so because there is a delta km here, this whole two summations are going to contract into one. So let's simply replace this with k upon k factorial. Okay, and so this is 0 to infinity 2r, and because k is equal to m were the only terms that were surviving, we are going to 2r dr e to the power 2k, sorry, r to the power 2k e to the power minus r square. And now we will make the, I forgot to write this here, and now we are going to make the standard substitution, which is r square, let's say, is equal to lambda. So first order approximation, we get 2r dr equals to d lambda. So this beautiful 2r dr will be directly replaced by d lambda, and r to the power 2k will be replaced by lambda to the power k, and this will be replaced by e to the power minus lambda. So k equals 0 to infinity k upon k factorial 0 to infinity d lambda e to the power minus lambda times lambda to the power k. And what is this integral equal to? We already know that this is the definition of gamma of k plus 1 or k factorial. So this integral is equal to k factorial 0 to infinity d lambda e to the power minus lambda lambda to the power k is equal to k factorial. Okay, so we can simply cancel this with this, and we get k equals 0 to infinity k. And we have already talked about this before. After all this heavy mathematics, we have come to this equation, and this is nothing but just equal to the identity. So what we have just proven is a very beautiful result indeed, that we want to write down the closure relation for the basis in terms of the coherent state basis. It's going to look something like this. So if you have got any doubts or got confused by something, try watching it again. And but I found this whole proof to be like extremely beautiful, and the way that these things cancel, and the way that this pi cancelled here, and then in the end we got the factorial cancelled here, and then this very simple closure relation came out. I found that to be pretty interesting. So I hope that you got to learn something from this video. I hope that this didn't get too rigorous, and thank you very much for watching.